Right, now we're going to explain the cosine function, right, or the cos function. Exactly as we did with the sine function, we will first start off with the parent function, then move to the cos function in a more generalized form. Because remember, if you're going to work with these functions or just the parent function, then we can't really expand our applications with it. Okay, so let's get started. To fully understand how the cos function came to be, we have to first test a few values of theta, thereafter plot the graph. We will intentionally restrict the domain of the function so that it exists from 0 to 360 degrees. This is due to the periodicity of sine, cosine, tan functions. I've said this before as well. We want to restrict the domain so that we can get the most information and complete information from the graph. So do I need to go more than 360 degrees and less than 0 degrees to get a complete view of the function? No, we don't, because it repeats itself. So if it's going to give us the same information over and over, let's just understand what it will do in one full cycle, right? Or between 0 and 360 degrees. In other words, these graphs will repeat itself over and over in these intervals. Remember, every graph we draw is the parent function. Thereafter, we will shift and stretch the function with other variables or constants, right? So the shift is what we call the translation, and the stretching is what we call the transformation. Okay, so we'll transform and translate. Right, so therefore we have the function y is equal to cos of theta. Yes, so now when we put in these values of theta, let's see what y values we output. When we put in 0 degrees, we get 1. When we put in 30 degrees, we get 0,87. 60 degrees, half. 90 degrees, 0. 120 degrees, minus half. 150 degrees, minus 0,87, and so on. And so at 0 degrees, we get 1. At 30 degrees, we get 0,87, which is approximately here. At 60 degrees, we get half, which is exactly here. At 90 degrees, we get 0. And if you do that for all of the points, and remember, you can do infinitely many points here. The more points you have, the more accurate your curve will be. But I just want to do it for a few points just to get a general idea of what the curve is trying to do, or what the shape the curve assumes. And so when you do that and you join all the points, it looks more like a cup, right? It has like this cup shape, right? If you join all of the points together. And so this is what the parent function looks like. Now, what's the important things that we need to remember here? Exactly like we did with the sine function and with the parabolic function. If you don't sketch the function, you won't understand how the function behaves generally, right? And so if I want to find the x-intercepts, exactly as I did with the sine function, the x-intercept is where y is equal to 0, right? And then I say cos of theta is equal to 0 degrees. Then theta is equal to the inverse of cos of 0, which is equal to 90 degrees, right? And so what happens here now is the calculator is only giving us one of the two answers that we're supposed to know, right? So because the cos function will behave like this generally, right? This is the way it behaves, the parent function behaves. So therefore, we need to know that it has two x-intercepts, one at 90 degrees and one at 270. There is no other way. There is no other way you master this but this way, okay? So you need to remember that. And then the y-intercept will be at 0 degrees, and then the turning point will be at 0, 180 degrees, and 360 degrees, right? And so this is what you need to remember. These are values that you need to commit to memory, right? So if you notice now between the sine and the cos function, it was 0, 90, 180 degrees, 270 degrees, and 360. So we're going up in nines, increments of, or 90s, increments of 90s. So 0, 90, 180, 270, and 360. Something happens. But obviously now for the sine and the cos function, for the sine function, it does this here. So if I go 0, 90, 180, 270, and 360 degrees, now we can see that 0, 180, 360 is what? The x-intercepts, and 90 and 270 is the turning points. For the cos function, right, for the cos function, if we go 0, 90, 180, 270, and 360, now you can see here now what's different. At 90 and 270, we have the x-intercepts, but at 0, 180, and 360, we have the turning points, right? That's the turning points, remember, is the extremes. So if you remember it, you basically sketch the basic shape of the function, and then you input these values, and then you analyze. Is that the x-intercept or the turning point? You have any problem that you're given, you have to sketch the parent function. There is no other way to remember it, right? Because your calculator will not give you all possibilities, right? It'll only give you one of the two or one of the many possibilities. So you need to do this. Right? This is what you need to commit to memory. This is why the high level questions are difficult, because you can't understand the basic shape of the function and what it's trying to communicate with us. Okay, your understanding of this parent function will heavily impact how well you understand this topic. As I said, to me, mathematics is fully understood with functions because it helps you visualize what these numbers mean. So it's the exact same thing here. We're trying to visualize what these numbers are trying to tell us, and this is what we have to know. Okay, so all the parent functions are extremely important. Even when we start to shift and stretch the function, we always start with the parent function. Remember, it was the parent function, then we went to the amplitude, and then we went to the shift. And I'll explain now. I'll give you a bit more of a detailed reason why we do this and why we do it in this order, but it's the exact same idea, right? It'll apply across the board. All right, so let's do the components of this function. And I've already mentioned it, but let me formalize everything so you can see it in one nice, neat summary. The domain and range. The domain of any function is the x values for which the function exists, right? It's the set of x values for which the function exists. Again, as I said, that we intentionally restrict the values of theta that we can input, but it can be infinitely many values that we can use. But we're going to intentionally restrict it because between 0 and 360 degrees is the interval that we get the most or all of the information that we need to know about the cos function. So we don't have to have it repeat many times. And so the domain for the cos function will be between 0 and 360 degrees. The range is a set of y values for which the function exists. By observation, you can see, right? It peaks at 1 and it troughs at -1. So the peak and the trough, we can see that the minimum value is -1 and maximum is 1. And we have to include both of those extremes. Okay? The x-intercept is the point at which the function intersects the x-axis, or where y is equal to 0. Again, you cannot get these answers by putting it on the calculator. You have to know the basic shape of the function. And so if I'm here now, and if I have to sketch the function, I don't have any visual reference of the cos function, but I know it looks like a cup, right? So I'll do this here, and then I'll start 0, 90, 180, 270, 360, right? And then I'll say, okay, where's the x-intercept? X-intercept, you know, by definition, is the point where the graph cuts the x-axis. So therefore, it'll be there and there, right? So that's the two answers there. And then your y-intercept is obviously the point where it cuts the y-axis. You can read it off there. It is 0 degrees. Again, even with the turning points. The turning point is the point where the function's y value either reaches a maximum or a minimum. See there. Maximum, 0, 360. Right? Minimum at 180 degrees. Very simple. Once you get this down here, you can get any bit of information from it. And then the period of the function, when we put in infinitely many values into the cos function, we notice that after every 360 degrees, it just continuously did the same thing over and over and over. So therefore, what we say is that the period of the function is 360 degrees, right? It will repeat itself every 360 degrees. And so if this function had to continue, like this here for the next 360 degrees, then this increment here, the distance from here to here, should be 360 degrees. Because one full cycle, this one full cup, is 360 degrees long. You could say along the x-axis. Okay, so that's what we mean by the period of the function. It repeats itself. We're going to make a lot of important conclusions from this. And this is, this is why I said that two different angles can output the same trigonometric value. I'm going to get back to that when we're solving term 1 problems. You'll see exactly what I mean. Okay, but for now, that's everything that you need to know for the parent function for cos. Everything, right? The most important thing that you need to take care is the domain, the intercepts, the turning points, and sketching the function so that you have a visual reference of what the parent function is and is trying to communicate. Right? That's very important. So we're going to move over to the cosine function in a more generalized form. Again, so that we can expand our applications with it. Right, so now we can talk about the cosine function in a more generalized form. Like all functions, the cosine functions can be expressed in a more generalized form. In the generalized form, we can shift and stretch the cosine function by either increasing or decreasing the values of the constant. Let's first express the cosine function in the generalized form and thereafter examine the effects of each constant. So there's it here, right? We know that the parent function takes on the form y is equal to cos theta, right? Now we're saying that the generalized form is y is equal to a cos theta plus q. Okay, so it is important that we examine y is equal to cos theta function as a parent function for cosine. Now let's examine the effect of a and q on the parent function. So remember, everything is relative to the parent function. I've said that repeatedly, right? So if we add in q, If you do something to this function, it first affects the parent function. Okay, so let's examine the effect of q. When we add y is equal to cosine of theta, let's do it for 0, 90, 180, 270, and 360, right? What we're going to do now is we're going to put these values in and examine the outputs, right? So this is with no transformation and no translation. When you put in 0, you get 1. When you put in 90, you get 0. When you put in 180, you get -1. When you put in 270, you get 0. And when you put in 360, you get 1. How do I know this? Because I sketched the function. There's it here. 0, 90, 180, 270, 360. Right, so now that's how I came to this conclusion. But now what happens is if we have a vertical shift, right, an up and down shift. So I added by 2. Now when you put in these values of 0, 90, 180, 270, and 360, see what happens. When I input 0, cos of 0 is what? It is normally 1, but now what are we going to do? We're going to add by 2, so now it'll output 3. When I put cos of 90 in, it is normally 0, but now because I add by 2, what would it become? It would become 2. Cos of 180 is normally -1. If I add by 2, it becomes 1. 270 is 0, now it'll become 2. Cos of 360 is 1, but now it'll become 3. Now if we sketch this function, we get the following, right? This is what the parent function looks like. Right, it starts at 1, ends at -1. This is 0, 90, 180, 270, 360. Right? But what's going to happen now is at 0 now it'll become 3. So if I extend this line up here, right, at 0 now it'll become 1, then 3 is approximately here. For 0 degrees it was 1, but now it will become 3. At 90 degrees it was 0, now it will become 2. So that's somewhere here, right? At 180 degrees it is -1, now it will be 1. So that's approximately here. At 270 degrees it is 0, now it will become 1. That's right here. And at 360 degrees it was 1, now it will become 3. And when you sketch the function, it assumes such a shape. And so remember how we discussed with the sine function. We said that the sine function is oscillating about the x-axis. Now this function here is going to oscillate about this line y is equal to 2. See the line y is equal to 2? It's oscillating about that point. Can you see that? So therefore you can see it'll just continuously do that. Go down, up, and continuously create that cosine function. So that's basically what the q value does. If it is positive, then it takes all of the outputs of the parent functions and it adds it by q units. If it is negative, then it takes all the values of the parent function and it deducts it by q units. Okay? Right, so if I go here and I show you, so this is the parent function and this is the function that we're about to translate. If you put positive values for q, see what happens. The function moves up. If we put in negative values, the function moves down. Remember, this is always relative to the parent function. Can you see that? So if I play it out here, you can see positive values, can you see it's increasing? Right, and then for negative values, see what it does. Shifts it down. So that's all we're doing. We're either shifting the function up or we're shifting it downward by q units. Right. And then if you look at the a value, what does the a value do? It affects the amplitude of the function. Right, exactly as we said, that the amplitude is basically the peak and the trough, or it's the displacement or the distance from the equilibrium to the peak or from the equilibrium to the trough. And so normally we have the function y is equal to cos theta. Let's just focus on these values here, right? These values here, 0 and 360 degrees. At 0 degrees, we normally get 1. At 180 degrees, we get -1. And at 360 degrees, we get 1. Now, I'm not going to put these values in because when you multiply by 0, you don't get any change, right? It'll just be 0. Now, if I put 2 cos theta, and if I put in these same values, see what happens. At these values, look at this. At these values, cos of 0 is what? It is normally 1, but now we're going to multiply by 2, it becomes 2. Cos of 180 degrees is normally -1, but if you multiply by 2, it becomes -2. Cos of 360 is normally 1, but if you multiply by 2, it becomes 2. And so what's going to happen is we're going to take this parent function and we're going to affect the amplitude, right? So what's going to happen is this here. This is going to come here. This -1 is going to come here, -2. And this 1 here is going to come here. Right? So all of the non-zero values will be multiplied by 2. But the 0 values will stay where it is, isn't it? Because it can't move. And so what's going to happen is now the function is going to assume such a shape. So what it did was it stretched the function. It stretched the parent function. Can you see that? So that's basically what we're saying. So if it's a value bigger than 1, like 2, 3, 4, 5, whatever, it'll stretch the function. Again, if it is a fractional value, like half, then all of the amplitude values will do what? It'll just basically multiply by half. So that'll be here, this will be here, and this will be minus half. And so when you join it, what it does, relative to the parent function, it compresses the function. Okay, then let's move over to the point where it is negative. If it is negative, then we have the following. Isn't we said when you have a negative a value, then it's reflected about the x-axis. So now this is what the cosine function looks like when it's positive, when it has a positive a value. If you reflect a point about the x-axis, you have to take this point, reflect it perpendicular to the x-axis and about the same distance away. So this point will come here. This point here will come here. This point will stay here. This point will come here. And if you do that for all of the points, see this point here will move in the opposite direction but the same distance. So it'll go somewhere here. And if you do that for all of the points that make up the cosine function, it's going to basically look like this here. See, the normal function goes down and then up. This one goes up and then down. Right? However you want to remember it. But this is the way I remember it, right? I think about reflecting it. So this is what the shape looks like. And then the same idea applies in the negative direction. If it is a number less than minus 1, then it'll stretch it. It'll stretch it, but in the negative direction. If it is a number that is a fractional value, but like minus 0,5, then it'll compress it, but in the negative side. Right? So all the negative does is it reflects it about the x-axis. But then when you analyze it, if it's bigger than 1, right, forget the negative. Let's say if you have minus 2. The negative does its effect by reflecting it about the x-axis. What does the 2 do? It stretches the function. But now because we have a negative, it will stretch it in the negative direction. If I had minus 0,5, the negative, what it does? It flipped the function, right? So ignore that part. What will the half do? The half would compress the function or contract it, but in the negative direction. Can you see that? Because we have the negative. And so if I do this here, now look at this. This is the parent function. This is the function with the a value. Can you see what happens? It stretches the function. You can see where all of the values are 0. See, 0 and 0. It stays there. Everything else will get multiplied, but only the 0 values will stay. Right? And then when you go in the negative direction, it flips. Can you see that? It flipped. Can you see that? It flipped. It flips. Right? And so if you look at it from a different perspective, when you're talking about negative values, think of the cosine function as a negative parent function. So relative to the negative parent function, what's happening to the function? Can you see that? It's compressing it, compressing it. But if you go bigger values bigger than minus 1, can you see what it's doing? It's stretching it relative to the negative parent function. So this is going up and then down, right? But when you have a positive parent function, it goes down and then up, right? So positive values, you can see how it behaves. All the negative does is it flips it or reflects it about the x-axis. Okay, so that's the effect of A. Again, if you want to find the value of A, or what the definition of A is, it's basically the distance from the equilibrium. See, this is the equilibrium to the peak or the trough. See, it's this distance here and this distance here. So, for example, here the amplitude is what? 1. Because it's from here to here is 1 and from here to here is 1 unit. Can you see that? So that's how we do it. And remember, it has to always be positive because it's a distance value. Okay? But how do you get it? Right? How do you get the amplitude? So let's say you were given a complicated example, right? Let's say that we don't know what it is. And the amplitude is what we need to find, right? And let's say that the function assumes the shape here. It's oscillating about the line 5. Y is equal to 5. It has a peak of 7. It has a peak of 7 and a trough of 3. So how do you find the amplitude? The amplitude is A is equal to the peak minus the trough divided by 2, which will be 4 over 2, which is 2. And so if I have to write this equation for this function, it'll be y is equal to, you see the way you do this, right? You'll say y is equal to 2 cos of theta plus 5. Right? Now I'm going to show you how we can extract information given the graph, and we need to find the equation. I will show you how we can do that. But for now, I'm just showing you that the formula for amplitude, right, for both the sine and the cos function, it is A is equal to the maximum minus the minimum divided by 2. That's the formula for amplitude. Okay, we will get to much more complicated examples, right? Things that are a bit more thought-provoking. You need to think about these things deeply. But for now, you can see It'll be maximum minus the minimum divided by 2. Okay, so yes, that's everything that we need to know there for the amplitude. Now let's go over to the components of the generalized cosine function. Again, the domain for it will be between 0 and 360. That's all. At grade 10, it'll be literally that simple. Why? Because we get the complete idea and image of the cosine function when it is in this interval. Could we go higher? Yes, we could, but we don't need to because it repeats itself. The range of the function is the y values for which the function exists. Since the constants a and q will both affect the range of the cosine function, right? Meaning it will affect the maximum and the minimum value for which the function exists, we have to find a generalized formula that we can use when we given vertical shifts and vertical stretches. So if the function is shifted up, it'll affect the range. Or if the function is stretched out or compressed, it'll affect the range. Okay? So how do we do it? We start off with a known fact. We know that cos of theta, see, cos of theta is the y value. See, when we say y is equal to cos of theta. So if y is equal to the cos of theta, then y is the same as cos of theta. So we can start off with this fact here. We know that the y values of the cosine function and the sine function oscillates between these two extremes. And so what we can say is, we can do that. Then if we bring in, let's say, we bring in some value of a, whatever the value is. Remember here we're generalizing. So I'm saying given any a value, we can make this statement. If I multiply this, then I need to multiply that and that. And we do not change it, we re-expressed it. We do not change the inequality, we re-expressed it. Why? Because if I divide by a throughout, if I take this a and divide by a on both sides, I will get back to this fact. Not changing anything. Right? Then, right? And so if we do that now, look here. This is the parent function. If we multiply by a, this is the parent function. If we multiply by a, from it being 1 now, it goes to a and minus a. Can you see that? It was normally 1 and minus 1. Now it'll be a and minus a. So the range of this green function now will become what? A and minus a. It'll exist between these two extremes. Okay, would you agree? Right, perfect. Now let's say that we shift this function up. We shift the function up. So all these values, and don't worry about every other value, just focus on the extremes. All these values, these extremes, will now shift up by plus q. We're going to add q. So doesn't we say we add q to every value? So from here now it'll go here. From here now it'll go here. This value will add by q, it'll go here. This value will add by q, it'll go here. This value will add by q, it'll go here. And so when you join all these values together, this is what we get. Can you see that? Or mathematically we write, if I take a cos of theta and I add q, I must add q on both sides. Remember, if I subtract by q here and subtract by q here, I'm left with this. So we're not changing it, we're re-expressing it. And so now the function will oscillate between whatever this a value is plus q. So if this was 3 and we shifted the function by 2 units, now from being 3 it'll go to 5. If this was minus 3, if we shift it by 2 units, it'll be minus 3 plus 2, which will be minus 1. So now it'll exist between 5 and minus 1. Can you see that? But we write it mathematically and we can generalize. This is why maths is so powerful. Because if you use the logic, then it should exist for all values. By us saying a and q, it's saying I can input any real value here, and this statement will still be true. Right? Any real value. There is no restriction. Because if there was, I would have stated it here. But I'm not. So this is why you can use this as a general formula. So if they ask me, let's say they gave me a question. Y is equal to 5 cos of theta plus 3 is the function. What's the range of this function? If they ask me what's the range of this function, I can do one of two things. I can first sketch the parent function, then sketch the amplitude, right? Or affect the amplitude and then affect the shift. And then find out what my max and min would be. Or I could just follow this formula here. The minimum value is, right? The minimum value is what? The minimum value will be minus 5, right? Minus 5 because that will be the minus a, right? Plus q will be plus 3. And the maximum value will be 5 plus 3, right? And the outputs could be any real value. So f of theta could be an element of real. And then I'll say f of theta is an element of, from minus 5 plus 3 is what? Minus 2. And 5 plus 3 is 8. Can you see that? Now, if I want to do it, let's say this is not something that doesn't resonate with me. Let me convince myself then. Let me at least convince myself that this is the best way to do it, the mathematical way. I can see we can do it mathematically or algebraically, or we could do it visually. So visually, this is what I would do. I would say, okay, this is 1, this is minus 1. Then I'll affect the amplitude. Now from being 1, it'll go to what? 5. So it'll go to 5 and minus 5. The 0 values will stay 0, and this will go here. This one here will come here. So now it will look like this here. Can you see that? And then we affect the shift. Take all these points and shift it 3 units up. If I shift this 3 units up, what it becomes? From 5, it'll become 8. Let me just change the color here. From 5, it'll become 8. This value. From minus 5, if I add 3 to it, what will it become? Minus 5 plus 3 is minus 2. So it'll be approximately here. Minus 2. This value here, from being 0, what it'll become? 3. Somewhere here. This value will go here. This value will go here. But we don't worry about any other value. We just worried about the extremes, right? Just to make that known to you. And so now where the function is oscillating between 8 and minus 2. So I showed you 2 different approaches that can get you to the same answer. So if you start writing maths and understand this notation, trust me, maths at a higher grades will be a walk in the park. So you need to start doing this. Okay? You need to start doing this. If something, you're not finding something comfortable, or if you can't understand something, look at it from a different angle and convince yourself that this is the way. Right? Convince yourself by looking at it from different perspectives. Don't convince yourself by just saying, you know, I need to get a distinction. Let me just learn it and just learn it as a rule or by heart it. It's not going to work. You can't commit these things to memory. You need to understand it. You need to understand it. Okay? With intercepts, again, there's no way you can just solve for this by putting it into the calculator. Right? We know the fact is the x-intercept is the point where y is equal to 0. And we know the fact is the y-intercept is the point where x is equal to 0. But what you need to remember is sketch the function. See how many times I sketched it just in this lesson? 0, 90, 180, 270, 360. And then when you have all of those shifts, now you need to apply it. Right? You need to apply it. But it's literally this simple. Right? It's literally this simple. And we're going to link it up to much more fancier sections so you'll get an idea. But for now, you can see what we're doing. Right, so now that we understand that, let's move over to the other components. Let's talk about the turning points. How will the turning point on the translated and shifted function be affected? Again, if we do the exact same and follow the exact same logic, what happens to the maximum point? Let's look at it. It's going to basically follow the same idea as we did for the range, isn't it? Because the turning point is basically the highest and the lowest. It's basically the peak and the trough, right? And the range is basically the peak and the trough. So how do we get the peak? Is basically a plus q. But now it peaks at 2 points. When you sketch the function, you know it peaks at 0 degrees and 360 degrees. And we know that it troughs at 180 degrees. So it peaks at these values. What that exact y value is given by a plus q. Follow the exact same logic as we did here. First affect the amplitude, then do the shift. Exact same logic. Understood? And then when we talk about the turning point, the minimum value, right? How do you get the minimum value? It's the same as the minimum value from the range. Has to be the same. It has to be the same, right? But where specifically, what's the x coordinate? It's 180. How and why? Because it comes from the parent function. The parent function said so. Understood? So that's how we're going to deal with these stuff. This stuff is very simple, right, at grade 10, because at grade 11, we start dealing with left and right shifts. So now your value, the x coordinates will differ. Right, but for now you understand the y coordinate as the amplitude plus the q value, or the negative of the amplitude plus the q value. And then the period of the function, same story. Every 360 degrees the function completes one cycle. So this here to here, this distance here should be 360. Right, from here to here, this should be 360 degrees, because every 360 degrees we have one full cycle. Can you see that? So it's literally that straightforward. Right, just to re-emphasize and ensure that you guys understand this. If I'm trying to find the turning point, right, I'm going to literally do the exact explanation that I did here, right? But let's just do it just so that you understand. If I try to find the turning point, let's say for the function y is equal to 5 cos of theta plus 3, then what I would do is I would first sketch the parent function, right? This is the parent function. That is 1, that is minus 1, right? Then we'll affect the amplitude. If you affect the amplitude now, it'll become 5 and minus 5. Let me just extend this here and take this up there. Now it'll become 5 and minus 5. And then if you affect the shift, right, all of these values, so now the function will look like what? It would look like this here. And then when you affect the shift of it, then all of these values will get added by 3. So can you see what we did? We first affected the amplitude. We took the amplitude value and then we added the q value. If you add by 3, this will become 8. This will become, if you add by 3 here, this will become minus 2. This will become 8. This will become 3, this point here, because it's 0. 0 plus 3 is 3. This is 0. 0 plus 3 is 3. And if you join all of these points together, can you see what we get? 8 and minus 2, which is the same as just saying a plus q and minus a plus q. See, minus a is the same as 5 times minus 1, which is minus 5. So it's the amplitude, but on the negative side. And then if you add by q, you're just saying it's this plus the whatever the shift is, or minus whatever the shift is. Same logic, right? It will apply even in the negative direction. So yes, it's literally that simple. We literally use the exact same logic as we did here. But it shouldn't be surprising to you, because the range comes from where? From the turning points. It comes from the maximum and the minimum. It comes from the maximum and the minimum. So whatever you get here for the range, you should get the same for the turning point. Has to be the same. Okay, so that's everything that we need to know for the cosine function.